Hey there, it's Nova, your digital guide to the wonders of technology on AI Unplugged. Quick question for you. Have you ever tried to imagine a computer that doesn't use ones and zeros? Or maybe one that uses both simultaneously? Well, hang on to your neural networks because today we're diving into the mind-bending world of quantum computing. You know how your smartphone struggles when you have too many apps open? Imagine a computer that could simulate entire molecular structures or break encryption codes that would take classical computers longer than the age of the universe to crack. That's not science fiction. It's quantum computing in 2025. Today, I'll walk you through how these reality-warping machines work, the major breakthroughs we've seen this year, and what it all means for your future. Whether you're a tech enthusiast or just curious about what's coming next, this episode will transform how you think about computation. Let's start with a question that might be bouncing around your brain right now. What exactly makes quantum computers so special? To understand quantum computing, we need to explore some truly bizarre properties of our universe that exist at the tiniest scales. Classical computers, like the one you're probably using to listen to this podcast, work with bits that are either 0 or 1. It's a binary world. But quantum computers? They use something called qubits. And here's where reality gets weird. Qubits can exist in both states simultaneously, thanks to a phenomenon called superposition. Think about it this way. If I flip a coin, it lands on heads or tails, but a quantum coin would somehow be both heads and tails until you actually look at it. Sounds impossible, right? Yet that's exactly how particles behave at the quantum level. And it gets stranger. Ever heard of entanglement? When qubits become entangled, they develop this spooky connection where changing one instantly affects the other, even if they're galaxies apart. Einstein called it spooky action at a distance, and he wasn't kidding. Now you might be wondering, Nova, why should I care about these quantum peculiarities? Well, here's the thing. These properties allow quantum computers to explore multiple solutions simultaneously. 2 qubits can represent 4 values at once. 3 qubits can represent 8, and so on. Scaling as 2 to the power of n. This exponential scaling is the secret sauce that makes quantum computers potentially millions of times more powerful than classical machines for certain problems. Now let's talk hardware, because the race to build better qubits is absolutely fascinating. Building qubits isn't easy. These quantum systems are incredibly fragile. Just looking at them, metaphorically speaking, can make them lose their quantum properties. This is called decoherence, and it's the archenemy of quantum computing. Different companies are taking different approaches to building usable qubits. IBM and Google use superconducting circuits that need to be cooled to temperatures colder than outer space. We're talking about a fraction of a degree above absolute zero. Can you imagine maintaining that kind of environment? Your freezer at home suddenly doesn't seem so impressive, does it? Other companies like IonQ trap individual ions with electromagnetic fields. These trapped ions maintain their quantum states longer but operate more slowly. The big breakthrough of 2025, though? That would be Microsoft's Majorana 1 processor with its topological qubits. Now, I know topological sounds like something from a geometry class you'd rather forget, but this is genuinely revolutionary. These qubits use exotic materials called topoconductors that are naturally resistant to errors. Imagine trying to store information by tying knots in a string. The information isn't stored in any single part of the string, but in the overall pattern. That makes it much harder to accidentally erase. That's roughly how topological qubits work, and they could be the key to scaling quantum computers to millions of qubits. You might be thinking, this all sounds very theoretical. But here's the reality check. Companies like D-Wave are already using quantum systems to optimize shipping routes and reduce fuel consumption by 15%. Pharmaceutical giants like Roche are simulating molecular interactions that would take conventional computers months to calculate. The quantum future isn't coming, parts of it are already here. But there's a massive elephant in the quantum room: errors. Let's talk about why quantum error correction is perhaps the biggest challenge in the field. If you've ever had your computer crash in the middle of an important document, you know how frustrating errors can be. Now multiply that frustration by about 1,000, and you'll understand the quantum computing dilemma. Quantum states are incredibly fragile. Cosmic rays, tiny temperature fluctuations, or even mild vibrations can cause qubits to lose their quantum properties. It's like trying to balance a pencil on its tip during an earthquake. Incredibly difficult. Researchers tackle this through quantum error correction, which essentially spreads quantum information across multiple physical qubits to create more robust logical qubits. The breakthrough of 2025 came from Quantinuum, which demonstrated a logical qubit with a lifetime of 10 seconds. That's 100 times longer than their physical qubits could maintain coherence. But here's the catch. Current error correction schemes are incredibly inefficient. We might need thousands of physical qubits to create just one error-protected logical qubit. You can see the scalability challenge here. It's like needing 1,000 pencils carefully arranged to balance one virtual pencil reliably. And that's not the only challenge. Quantum computers need massive cooling systems that consume enormous amounts of energy. A single dilution refrigerator uses about 10 kilowatts, enough to power 20 average homes. We're essentially building mini power plants to run these quantum systems. There's also a global shortage of quantum talent. The industry needs over 50,000 skilled professionals, but universities are only beginning to develop quantum computing curricula. Have you ever thought about a career in quantum computing? The field is wide open for passionate pioneers. But perhaps most concerning are the security implications. Which brings us to our next topic. What happens to encryption in a post-quantum world? Remember when you set up that secure password for your email? The encryption protecting your digital life relies on mathematical problems that are extremely difficult for classical computers to solve. But quantum computers could potentially crack these codes in hours. This has led to a strategy security experts call harvest now, decrypt later, where malicious actors collect encrypted data today, planning to decrypt it when quantum computers become powerful enough. Pretty unsettling, right? Your encrypted messages from 2025 could be read in 2030. That's why organizations like NIST are standardizing post-quantum cryptography, encryption methods that even quantum computers can't easily break. But implementation will take years, creating a window of vulnerability. Beyond security concerns, there are serious questions about equity and access. The nations and corporations that control quantum computing technology will have tremendous advantages in everything from drug discovery to financial modeling. If you think the digital divide is concerning now, wait until some countries have quantum capabilities while others don't. Then there's the environmental impact. As I mentioned earlier, quantum computers are energy-hungry beasts. As we battle climate change, we need to ask if the quantum advantage justifies the environmental cost. Companies like PsiQuantum are working on photonic quantum computers that might operate at higher temperatures, potentially reducing this energy burden. But it's not all doom and gloom. Quantum computing could help us develop better solar cells, more efficient batteries, and even carbon capture technologies. The same power that threatens our digital security could help solve our climate crisis. So who's funding this quantum revolution? Let's follow the money. The quantum computing race is heating up with massive investments from both governments and corporations. The U.S. Department of Energy announced a $65 million investment this year, targeting quantum software and control systems. The European Union has committed $1 billion through its quantum flagship program, aiming to develop a 100-qubit quantum simulator by next year. Tech giants are all in as well. Microsoft, IBM, Google, and Amazon are pouring billions into quantum research. Meanwhile, startups like PsiQuantum and Rigetti are attracting hundreds of millions in venture capital. You might be wondering, when will quantum computers become mainstream? That's the trillion-dollar question. Most experts believe we're 5 to 10 years away from quantum computers that can consistently outperform classical systems on commercially relevant problems. But the field moves quickly. Microsoft's topological qubit breakthrough wasn't expected until the 2030s. What might quantum computing look like in your daily life? You probably won't have a quantum laptop anytime soon. Quantum advantages apply to specific problems, not general computing. But you'll definitely feel their impact. Drugs discovered through quantum simulations, financial systems optimized by quantum algorithms, and new materials designed with quantum computers will change your world in subtle but profound ways. Think of it like nuclear fusion. You don't need a fusion reactor in your basement to benefit from the clean energy it might someday produce. Similarly, quantum computers will likely remain specialized tools, accessible through cloud services, transforming industries behind the scenes. As we wrap up our quantum journey, let's reflect on what we've covered. Quantum computers leverage the strange properties of superposition and entanglement to potentially solve problems far beyond classical capabilities. Major breakthroughs in 2025, like Microsoft's topological qubits and advances in error correction, have accelerated progress, but significant challenges remain. The implications touch everything from cybersecurity to climate science, creating both opportunities and risks that society must navigate carefully. I find something deeply poetic about quantum computing. At its core, it's about embracing uncertainty and possibility rather than rigid binary choices. Maybe there's a life lesson there. The most powerful solutions sometimes come from accepting that the world exists in shades of probability rather than black and white certainty. Before I go, I'd love to know your thoughts on quantum computing. Are you excited about its potential or concerned about its risks? And if you found this episode mind-bending in a good way, please subscribe and leave a review. It really helps our quantum superposition in the podcast rankings. Until next time, I'm Nova, reminding you that in a world of ones and zeros, sometimes the most interesting state is both.